spontaneous tokamak rotation.
Thank you very much to the organizers for this invitation to be with you. I particularly enjoyed a number of the talks, but, and I enjoy the opportunity to try to communicate across different fields. So I'm trying to make this somewhat accessible to folks from the other fields than just the tokamak business. And I'll explain in a moment what is meant by spontaneous tokamak rotation. What I'll then do is talk about some of the scaling, the way this varies with plasma parameters. I'll talk about differences between the edge and the core of the tokamak, how it varies in time and space, and I'll make some very simple remarks about theory, and I hope we'll have a lot more about theory in the succeeding presentations today, so I'm not going to trespass on that too much. So my objective is really to say here are the experimental facts as we know them, and offer that as a stimulus to think more about this. So the starting point for tokamaks, of course, is that tokamaks, at least in an ideal case, are perfectly axisymmetric. The magnetic field, at any rate, is perfectly axisymmetric. If it is, then obviously toroidal angular momentum is conserved, and as a result, the magnetic field doesn't exert any force in the toroidal direction. There are, of course, nearby structures, the edge of the plasma, the machine itself, the vacuum system, and so forth, to which momentum could be transferred, but it can only be transferred if we have axisymmetric fields by the particles. Now, we know sometimes non-axisymmetric magnetic fields arise, either because we haven't made the magnetic field perfect or because the internal instabilities give rise to these. But most of the time, as far as we know, these effects are absent. By the way, the poloidal direction of rotation is quite different. Because the tokamak is not symmetric in the poloidal direction, poloidal rotation is rapidly damped, basically by the 1/r magnetic field variation. So we're usually talking about toroidal rotation. And neutral beams, which we've heard a lot about in the previous talk, are generally aligned with some substantial component in the toroidal direction, and therefore they naturally drive the tokamak to rotate. So here's an example from 1990, a long time ago, TFTR, where it was very dominated by toroidally injected neutral beams, which were able to heat the plasma, in this case it's ion temperature, to high temperatures in the center, and simultaneously gave rise to very rapid rotation, 600 kilometers per second, in the center of the region. By accidentally, it turns out to be the same velocity as the solar wind at 1 AU, in the same ballpark. And it was observed that in order to explain this rotation, one had to assume or deduce that the diffusivity of toroidal momentum, which is often written chi phi, so essentially this is the shear viscosity of the plasma, has to be of the same order of magnitude as the effective ion thermal transport, or perhaps a little bit larger. And in the mid-90s, following these types of observation, a commonly held view was that tokamaks rotate because of beams, and that the momentum transport is roughly diffusive. In other words, it's roughly speaking shear viscosity due to turbulence.
Ian, do you know what they use for a model to come to that conclusion?
No, I don't. No, I don't. Okay.
I assume it's pretty phenomenological.
It's very phenomenological, and I'll talk about phenomenological models a little bit later,
Do you know?
Peter.
It was measured, so they know how much torque the beam exerts.
Or was it measured?
I mean, fundamentally, they've got a source of momentum in the middle. It's being transported outwards, and it's something like the flux of momentum divided by the gradient of the velocity. Okay, is fundamentally what
The
it
velocity
is.
gradient evolved as the measurements improved. Really, they had a central rotation measurement. And the profile.
No. The profile here, these are measurements. Okay, the points are measurements. Okay. But in any case, this whole view was highly oversimplified one, even in those days, because the H-mode barrier was known to be a region of big velocity shear, and I'll come to that later. Before I do move on, though, let me just make one or two remarks about how you measure these velocities. Measuring the velocity is not all that straightforward, even though the Doppler effect on line emission is the dominant way of doing it. And the reason is because in the center of tokamaks, light impurities like carbon, for example, are fully stripped. And so the approach called charge exchange spectroscopy, or sometimes charge exchange recombination spectroscopy, was developed very cleverly by a number of people. And this works by looking across the neutral beams and allowing the neutral beams to provide one electron so that the light species become hydrogen-like, and then observing the lines from that. Now, the main point about that is you need a neutral beam in order to make charge exchange spectroscopy work. And therefore, these measurements have tended to be dominated by neutral beam heated plasmas like TF, TR, or D3D, or jet. If you want to look for spontaneous rotation, which is basically rotation when you don't have external sources of momentum, you need a different approach. Predominantly, folks have used Doppler spectroscopy of much higher Z impurities in which they may not be fully stripped in a natural way. For example, argon is often seeded. These are actually advantageous from the diagnostic point of view, in part because the diamagnetic term is smaller, going like 1 over Z, and also because their collisional coupling to the bulk ions is greater because of Z squared. There are also ways to diagnose the rotation by looking at perturbations that arise from various types of instability. And it turns out that the velocities you deduce from these, generally speaking, agree rather well with those that we measure from Doppler spectroscopy. So if you come to a tokamak like Alcator CMOD, which doesn't have any neutral heating beams, it is nevertheless the case that if one has, as we do, rather good measurements of plasma rotation, lo and behold, the plasma does rotate even though it's got essentially no internal momentum sources like beams. So for example, here's a shot where the stored energy is in the ohmic phase relatively low. You turn on ion cyclotron heating, which raises the stored energy in the plasma. Actually, a lot of that rise in energy arises from the fact that this plasma makes a transition from L mode into H mode here, and this is usually in the tokamak business monitored by monitoring the light at the edge of the plasma, which drops when you go into these high confinement mode regions. But the most important thing that I want to draw your attention to is that the velocity is small and slightly negative in the L mode phase, and it's rather larger and positive in the H mode phase. This is 10 to the fifth, so 100 kilometers per second. This amounts to a Mach number of about 0.3, not driven by beams or anything else, as far as we know. It's spontaneous. The profile of that velocity can be measured, and here it is in central, approximately half of the minor radius. So this is the magnetic axis, the center of the plasma, and this is about halfway out in minor radius. Yes?
Is positive rotation co-current?
Yes, it is. I'll make a remark about that on the next slide. And it's not uniform in the center. It's got a gradient. And actually, the measurements that we make, even though in some cases with rather large error bars, from the fluctuations more or less agree. So let's come to this point of it being co-current. You can verify that the direction of the current and also magnetic field in our device, because they're always in the same direction. When we reverse the current, we also reverse the toroidal field, is the thing which determines the direction of flow or of rotation. So if you put the plasma current in the negative direction, you have stored energy and ICRF power, and what you find is that the velocity which was in the same direction as the in the opposite direction as the current here, becomes in the same direction as the current here, and similarly, if the plasma current is positive, the velocity which was in the opposite direction to the current here becomes co-current in the H mode direction. So it goes from countercurrent to co-current. Yeah.
Are these single null diverters?
These particular ones are single null diverter
So the
situations.
grab-B drift relative to the diverter doesn't matter.
That's correct. The direction, the place in which the X point is doesn't matter. But in fact, I believe these reverse current ones were in both cases favorable. In other words, it was grad B drift towards the X point. So maybe I didn't answer you correctly. They are single null, but one is at the top and one is at the bottom. Okay. There are situations in which there are substantial non-axisymmetric magnetic perturbations which affect the flow. And this is an example. In this case, this is entirely an L-mode plasma. So in L-mode plasmas, we intrinsically have rotation which is a little bit negative. That means negative in this sense means in the countercurrent direction. But imperfections in the toroidal field can exert a force that is sufficient, provided the plasma slows down to almost zero velocity, that what we have is what's referred to as a locked mode. A locked mode is a situation in which the magnetic perturbation, instead of being shielded by the eddy currents that arise in the plasma as it's rotating, the plasma itself stops, the eddy currents themselves stop, and the perturbation can penetrate the plasma and it becomes locked. This is actually important from the diagnostic point of view because it verifies that we've actually got our zero of velocity measured right, which is one of the headaches with some of these high-resolution X-ray spectroscopy techniques. The advantage of charge exchange is that spectroscopy is done in the visible range, and you can use mirrors and lenses and so forth. This high-resolution X-ray spectroscopy with the heavy impurities is technologically more challenging, and so offsets are a bit of a headache. So this is an example where you have a large-scale magnetic perturbation which penetrates the plasma and does indeed exert a force on that plasma. And so it's an example of that. But rotating modes in general have far too small a torque, according to our measurements and calculation, for them to be particularly relevant. Now, when we first showed measurements like this with ICRF, one question naturally arose, well, perhaps this is really an ion cyclotron heating effect. So ICRF means in general these are so-called minority heating. We have a few percent minority of protons in a deuteron plasma, and we are damping the ion cyclotron waves on that minority. The minority itself can get quite hot. It can get up to tens or even hundreds of keV in average energy. And so we have an energetic tail on the distribution. Energetic ions in a tokamak have orbits that are either shifted relative to the magnetic surfaces if they're passing particles, or if they're trapped particles, they have these banana-shaped orbits like this. And if they're very energetic, those orbits can be rather large. And so one notion was that perhaps what one is doing is one is sort of preferentially scraping off ions, for example, on the outside. Co-moving, by the way, co-moving ions are always shifted outwards, and counter-moving ions are always shifted inwards. And so perhaps it's some effect like this which is driving the flow and transporting the momentum and causing this to happen. So basically we said, well, let's do the simplest thing we can think of, and that is to simply switch off the ICRF so we know we don't have these energetic ion tails. And it turns out that on CMOD one can get H modes without any heating other than the ohmic heating, which is always present because of the plasma current. And when we go into H mode like this, the plasma energy increases, the the electron density starts to accumulate, and lo and behold, the toroidal velocity, which was very small and in this case not noticeably negative prior to the H mode, swings positive, not as much, but still very substantially positive, and the sawtooth velocity essentially agrees with the argon. The argon measurements aren't very good here. You can see by the bouncing around of this that there were substantial uncertainties. That's one of the reasons why we were it was beneficial to have this independent measurement of the rotation. And so in this case, this is unequivocally spontaneous in the sense that there is nothing being done to this plasma that might be causing it to rotate. Now I'm going to move on now to talk about the scaling of that rotation. And the scaling of that rotation was actually a rather important extra piece of evidence in respect to this ohmic H-mode rotation. Prior to doing those ohmic rotation cases, we had built up a fairly substantial database of ICRF-driven rotation measurements, which are these red and the green points here. And what that database showed was that the toroidal velocity we see in H-mode conditions increases with this parameter, which is the stored energy divided by the plasma current. It's purely sort of engineering type of parameter at this stage, although I'll show you can turn this into physics in a moment. And what we saw from the ohmic rotation was that, lo and behold, those ohmic rotation points fall pretty much on the same curve. They're at the lower end of the curve down here, but they don't rotate as much because their stored energy isn't as great, because we're not applying auxiliary heating. But basically, they appear to fit the same scaling. So both ohmic and ICRF rotation velocity scale more or less the same. And from that, I think one can conclude that the bulk, at any rate, of the rotation is likely to be from the same mechanism, and that's another reason why we think this is very clearly spontaneous. Since that time, a lot of other machines have also been examined, and actually JET had seen similar phenomena almost concurrently with CMOD, maybe even earlier in some cases. But at any rate, a big database has been put together, and one tries to put together some kind of scaling which says how does the velocity scale with the parameters of the machine, and this is the sort of engineering scaling from all these different tokamaks, CMOD, D3D, Tor Supra, JT6D, JET, etc. And the scaling can be cast into something more like physics by thinking that perhaps what it really is that the Mach number, in this case it's been written as an alphane Mach number for reasons that I'll mention in a moment, but you could equally well have put it as a sound speed Mach number, is something which increases with beta, and also it's dependent on the Q factor. That's this helical parameter which governs the pitch of the helices. And if you believe the scaling, which isn't a terribly good scaling, and you try to extrapolate it to eta, which is what we all try to do, because one of the things we're trying to figure out is how will eta rotate. It actually turns out that eta will rotate somewhere up here. So it'll actually rotate at a very substantial alphane Mach number. That's actually terribly important for other reasons. For example, whether or not the conducting surfaces around the outside of a tokamak act to stabilize MHD modes is governed, we think, by some critical value of the alphane Mach number. And if eta does indeed rotate this rapidly, it will probably behave in such a way that that stabilization will be effective. Yeah.
Does the equal sign in the left figure mean that it does not depend on other non-dimensional parameters like rho star?
It means that that's what the scaling is, okay? But whether it does or doesn't depend on those other things.
But on the right-hand side, you would have normally pulled out some sort of rho star. So the question
I think
is,
the answer is we haven't got enough information to tell, okay, is whether it depends on other things. But that's what that scaling is, okay?
But even on that scaling, I mean, the CMOD cones do not seem so much
It's not a great scaling. That's what I said. It's not a great fit, quite frankly. And I'll show you some reasons why later. Because in fact, there is no universal scaling. It depends on a lot of things that we don't understand. So I'll come to this later. Let me just, for those who aren't experts, explain why this issue for ITER is so important. In ITER, in order to get neutral beams to penetrate, you need to have energies that are probably 10 times higher than the neutral beams that we heat current tokamaks, even jet, with. And in some cases, even that may not be enough. And so ITER may, in fact, in the end, be heated not by neutral beams, but by RF. If that's the case, then we won't have the strong neutral beam flow drive that Peter explained to us was so important for those high confinement modes. So what the spontaneous rotation of ITER is actually a very important question.
Quick question, on the left-hand scaling, is that Q to the plus 2.3 or minus 2.3?
It's Q star to the plus 2.3.
Presumably with that title, you're going to tell us why you care about those beams penetrating. Why not just drive edge rotation?
Yeah. So maybe it'll become clear. Okay, so I've mostly been talking about the toroidal rotation of the central region of the tokamak. When one goes into H mode, and this is an example as a function of time of going from L mode into H mode, back into L mode, and back into H mode again. When those transitions occur, actually the edge also rotates very rapidly. Roughly speaking, the direction in which the edge rotates, as far as we know, is in this direction. At any rate, the measurements that is being shown here is a rotation, which is basically it's the perpendicular component of the rotation, and its toroidal projection is in the negative direction, and that's why I've written it as negative here. At any rate, the point is that it isn't just that the whole of the tokamak rotates like a solid, nor is it even that there's some very simple diffusive profile of toroidal velocity from the center to the edge. There's a lot of action going on at the edge, which has been known for a long time, but is in a certain sense, as far as we know, spontaneous. Let me show you some examples of high-resolution measurements of these velocities at the edge of CMOD. There are many such measurements also at the edge, for example, of D3D and to a lesser degree in jet and some other important tokamaks. So these are not unique, but they are interesting. Let me just point out the scales here. This dashed line is essentially the last closed flux surface, so that's where one can think of the edge of the confined region as being. These are millimeters, so that's 1 centimeter, 2 centimeters, 3 centimeters there. So these are very high resolution measurements, about 3 millimeters resolution. This is the temperature profile of the boron 5. These are charge exchange recombination measurements. As I said, in general, CMOD doesn't have heating beams. It doesn't have heating beams at all, but it does have a much lower power, perpendicularly directed diagnostic neutral beam, which doesn't substantially affect the rotation because it has a negligible amount of momentum. This is the temperature profile. This is what's called the H-mode barrier. So this is an edge transport barrier, for those of you who aren't experts. Peter talked about internal transport barriers. This is a very familiar edge transport barrier, which is the signature of the H-mode. In CMOD, this barrier is very thin, about 5 millimeters. The density profile of boron 5+ is like this. It's also very steep. It actually seems to be slightly inside of the temperature barrier. But these are the quantities that I most want us to focus on. These are the measurements of the boron 5 toroidal velocity, this profile here, and pulloidal velocity. This work is all done by Rachel McDermott. The point to observe here is that there is a lot of structure, particularly in the last centimeter of of the profile in the poloidal velocity, although quite surprisingly there doesn't seem to be so much structure in the toroidal velocity at the edge of this. Now,
You said earlier that the toroidal velocity went negative at the edge, but did I miss either?
well, I didn't say that, but I might not have been clear. I said that we measure a perpendicular velocity, and if you were to take that perpendicular velocity and project it in the toroidal direction, it would have a negative component. Okay, and that's a subtle distinction that's important. Okay, yes.
How big would be the correction to go from the Born?
I'm just about to address that. Bulk velocity is what you want to know. Yes. So this is the boron 5 velocity. The boron 5 does not move at exactly the same speed as the bulk ions, which are deuterons in this plasma. So the question is, how fast are the deuterons going? And I'll come to that just in the next view graph after that. The way we get to answer that question is to discuss this radial force balance equation, which has been already talked about a couple of days ago in this conference. So the radial force balance says that the electric field in the radial direction has to balance the sum of the diamagnetic, the toroidal, and the poloidal components. This is V cross B, these two components together, and this is the diamagnetic term of the impurities, okay? In these are all the impurities, in this case boron 5. And here is this force balance. This is the radial electric field, and that is deduced as being the sum of the toroidal component, the poloidal velocity component, and the diamagnetic component. And so what you see is that the E radial has a very big negative dip at the edge of the plasma, although actually it's riding sort of high and positive in the center, and it goes negative down here in the edge. We've seen deep wells, so these are often referred to as ER well, the radial electric field well. We've seen wells in CMOD as deep as 200 kilovolts per meter, which is an extremely deep well, but this is not such a deep example. So what you might say is that the boron 5 plus pressure gradient and poloidal velocity are both contributing here to the ER well. And the ER force on the impurities, actually, it turns out, more than overcomes their pressure gradient at the edge. So in a certain sense, the electric field pulling the impurities back in at the edge of the plasma is more than sufficient to balance their pressure gradient at the edge of the plasma. And the toroidal velocity is approximately uniform with that offset. When you come to then try to deduce what the deuterons are doing, we don't have independent toroidal and poloidal measurements of the deuterons. So all we can do is we can say we know we've measured ER, and I've just shown you that complete measurement, okay? And we can compare, and we also know what the diamagnetic term from the bulk is. What we don't know then is what the direction and what the direction of the perpendicular velocity actually is. But what you can say is let's compare the ER well, which is what we just were discussing, deduced from charge exchange recombination. Compare that with the main ion diamagnetic term, which is deduced from the gradients of the deuteron temperature and density. And when you look at them, it's remarkable how similar the shapes of these two things are. Okay? I mean, there is a shift of about 10 kilometers per second perpendicular velocity, which we don't know whether it's toroidal or poloidal, but nevertheless, the shapes are very similar. So what we say is, in the H-mode barrier, the deuterons appear to be mostly confined by the electric field. That's one way to think about this. And there are really only relatively moderate, uniform, perpendicular D plus velocities across this region.
A question, what is the gyro radius in this edge, in the pedestal region?
Yeah, it's typically less than this sort of 3 to 5 millimeters, but not that much less. The poloidal gyro radius might be, a millimeter or something like that. So actually, it's not at all clear the extent to which gyrokinetics ought to work properly here, but it's on the borderline of
Well, you said the ploidal gyro radius is a millimeter.
right.
So the gyro radius is still
It's smaller than that.
Yeah.
But of course, because there are big gradients of temperature, you've got to ask yourself, well, where do you care? Okay, the temperature's varying by a very large factor
That's
across.
the boron temperature. That's
Yeah, but this is also
Back-
probably a very good measurement of the deuteron temperature. In the T's are better coupled than the V's. Let's put it like that. Okay. So if you try to put together then a composite picture of how does this rotation, which is essentially spontaneous rotation, all of it as far as we know, vary as a function of space from the magnetic axis, the center of the plasma, out to the edge. And I'll express it just in terms of this E radial, which is giving rise, of course, to the V cross B by being crossed with the magnetic field. Then it looks basically like this. So the high resolution X-ray spectroscopy gives us a profile of ER something like this. And the charge exchange spectroscopy that I've just been discussing gives us this well at the edge and then this positive value. And they approximately seem to meet together, at least within the error bars, which are pretty substantial error bars. Okay, these are not all that straightforward measurements to make. And so this is a very typical looking radial electric field profile for the spontaneous rotation. However, although this is typical, it's not always like this. Yes?
If you were to weight this by the mass, which of course is small in the middle and large at the edge, is the angular momentum net integrated over the whole thing more or less zero or not?
You're arguing that this negative blip might outweigh this? The answer is
Big
no.
volume.
No. Quick answer is no. The total, the volume here is not nearly enough to compensate for all of this volume. Okay.
But that's 0.7. Where's the middle of the machine? Oh, that's at the magnetic axis.
That's the axis here. So this is a centimeter or so of negative, and all of the rest of this, 20 centimeters or so, is
That's a
positive.
big volume effect. There's hardly
No,
any volume.
not that much. Not that much.
Okay.
By a long shot. But in any case, I don't think that's an important question, because right at the edge of the plasma, you've got neutrals, you've got interaction with the diverter modules, and so on and so forth. So there are very strong effects that happen just at the edge that can make the total momentum of the plasma non-zero, even if there's no magic way of getting momentum into the middle of the plasma. Okay, but as I say, this is typical, but it's not universal. And so I want to move on to transients, talk about heuristic transport and variability.
Sorry, could I just ask a question?
Yeah.
If you overlay a temperature profile on that, do they look completely uncorrelated?
Well, temperature, of course, peaks in the middle, and the electric field goes to zero.
You want temperature gradient is what he meant.
Yeah, so maybe what you mean is what's the velocity look like? Okay.
Well, yeah, but I'm saying if I look at the two profiles, will it strike me that they know about each other?
I think
Just visually.
in general the answer is no. Let me answer it by pointing to these profiles. Here are a set of essentially static profiles of toroidal velocity. And there are cases where the toroidal velocity is really quite peaked in the center, like this. There are cases where the toroidal velocity is rather flat, but non-zero, okay? And there are cases where the toroidal velocity is positive here and actually hollow and goes slightly negative, if anything, in the center. And these occur for different types of discharges. So these are two different types of H mode, and this, it turns out, is an internal transport barrier type discharge, not exactly of the type that Peter was talking about, but I won't go into detail about that. So the first thing to recognize is that while I've shown you a typical case, it is by no means universal, and we can make this change, and I'll talk about some other ways in which we can make this change. What I did want to say, though, was to talk about some transients Okay, so these are variations, if you like, static variations, but I wanted also to talk about transients. When we make this transition into an H mode, which occurs at this point here, we find that all of the velocities across most of the profile rapidly increase, but they don't increase all alike. So if you look at the edge of the plasma, let's say r over a equals 0.6, the velocity rises rather rapidly. But if you look at the center of the plasma, for example, this red point, the velocity takes much longer to rise than it does at the edge. So what's happening is you have this transition at the edge of the plasma. This edge of the plasma starts to rotate much more rapidly, but it takes time for that effect to propagate into the center. Now you can therefore do some kind of heuristic analysis to deduce how quickly that change is diffusing inwards. And you find, as has been found for situations in which you directly have a source, such as the TFTR case that I showed you, that the diffusivity that you need is in the ballpark of a couple of times the total thermal diffusivity. So that kind of confirms that there is a diffusive effect here. But of course, there has to be more than a diffusive effect. Otherwise, we would always just see flat profiles like this. In other words, if there was nothing but diffusion and a boundary condition, you would always just have a profile that was flat everywhere, which we know we don't have, especially since, as I've shown you, at the edge, all sorts of peculiar things happen certainly to the perpendicular velocity.
Ian, why do you assume that's diffusive? Couldn't you just as well say this is due to the change in the transport that's propagating? In other words, your transport's getting good at the edge, and that good value.
I guess I don't understand the question. Okay. I mean, if you adopt, let me just talk about this view graph, and then I'll ask you a question again if it's not become clear. Let's try that. So, in order for us not to have a flat velocity profile, which is what you would have if there was nothing but shear viscosity or momentum diffusion, you have to have some other term. And it's become a common, but I think bad habit for people to talk about something called a momentum pinch. Okay? A momentum pinch these days usually refers to something like this. Here, if you think about the flux of parallel or toroidal momentum across the field, heuristically this might be thought to have some kind of diffusive term, which is shear viscosity. And this thing which people call a momentum pinch is usually written in the following form here as being some coefficient times the toroidal velocity. This heuristic approach, in my view, has very little to recommend it. There's actually no good reason to make this term proportional to the toroidal velocity. You have to have this term, because if you don't have this term, then all that will happen is in steady state with no momentum sources, you'll have a flat velocity. So we know there must be terms in addition to this one, but my argument is it shouldn't be assumed to be proportional to the toroidal velocity. Actually, there are very good reasons why you should not assume that. For example, a term like this can only arise from Coriolis and centrifugal forces by Galilean invariance. Now, we're going to have some complaints, so I've stimulated some comments here.
No, this is actually, there's a lot of people in the room who aren't tokamak people, so I want to make two observations. On the previous slide, you said that you needed a D, which is this D on this page, on the order of the chi.
Right, exactly.
And the chi is much larger than the collisional processes can give rise to. And the D is even larger relative to its collisional value. So this is a turbulent process we're looking at.
Yeah, exactly. This is turbulence.
And
but we also think this is turbulence, right?
Yeah. And now the second thing is, so we're not thinking of anything simple like a fixed law. And now that D could have quite a bit of parametric variation in it. And so, in fact, we shouldn't be thinking that D is a constant, and we shouldn't be thinking it's coming from collisions. I just wanted to help
Okay.
people.
There was another comment or question here.
Yeah, I would say you present it as if it's an assumption, but it comes from the theory like this. It's not an assumption, and in fact it is indeed exactly the Coriolis force that generates a term like this.
Okay.
You can't say it can only be generated by the Coriolis force. In fact, it is generated by
Yeah.
the Coriolis force.
So let me clarify. Okay, so let me clarify my point again. There may well be terms that consist of momentum flux up or down the velocity gradient that are not driven by the velocity gradient. In other words, in some kind of Onsager viewpoint, these are off-diagonal terms of some type. My argument is simply that there is no reason to suppose or assume that they should be proportional to the velocity. So I'm well aware that there are theories that describe these forces, and they are very self-consistent. They depend on the Coriolis force. Those theories may be interesting, and they probably are very important in situations where you have strongly driven plasmas, such as jets. And so maybe they're important in that situation. But for spontaneous rotation, they can't explain it. For example, they can't possibly explain a situation in which there is the sign reversal of the toroidal field. So as far as I'm concerned, while these terms like this may exist, they are not the types of terms we're looking for to explain what I've called spontaneous rotation. And I think if we want to take some heuristic view, which I think will have many critics in this room, and probably in the end we should not take this heuristic view, but you've got to do something simplified to try to relate the experiments to the theory. Then what one ought to have, and here I put it in terms of a momentum conservation equation, is a term which is diffusive. You would also have to have a term which satisfies Galilean invariance, and then you would have a term which would be of this form, but the V0 here would not be the toroidal velocity, it would just be a convenient normalization. It might be just be thermal. In other words, this would be something which would just say that there is indeed a flux of momentum independent of the gradient of the velocity. In other words, that it's not a shear viscosity. And the reason for writing these heuristic things down is that you can, from the kinds of experiments that I showed you, transient experiments or indeed source experiments, deduce the values of D and V, these things here, but only if they are assumed to be invariant, which is the point that Bill was making. So if you assume, quite arbitrarily, okay, that these things are invariant, then you can deduce them from transients. But if they aren't invariant, and frankly we've got no reason to suppose they are invariant, then you've got grave difficulty unambiguously deducing even what these heuristic parameters are. Yes?
It may be worth remarking here, though, that equation has to give us a radioelectric field in the steady state. So there are real complications involved in all of those coefficients.
Absolutely, you get no argument from me.
One other, in that equation, in a uniform plasma with no gradients, you can't have any fluxes. If you're in thermodynamic equilibrium, you can't go out of thermodynamic equilibrium. So that VV in the last term must depend on temperature gradients or density gradients or other
exactly.
factors.
So in that sense, it comes from off-diagonal terms in an Onsager matrix. Exactly. Good point. Yeah.
Given that we think the turbulence depends on the flow and the shear in the flow, is it not reasonable to then take a step further and say that the D is going to depend on the flow, and then that equation we have in the top could be some horribly complex
Absolutely.
Non-linear function of velocity, which could quite easily exhibit bifurcation if we knew what D of V was.
Yes, yes. So certainly there's no reason to believe that these things are independent of V.
Yeah.
Yes.
In particular, D could have something that looked like V minus V crisp.
Could.
And then you can also, there's two ways to make that diffusive term zero. One is the
Well,
gradient zero, and the other one is
I
the
think
V.
there are arguments which say it's actually not the value of V toroidal that counts. It's probably its shear. And again, it comes back to this argument that the absolute value of V toroidal affects only things that really arise from Coriolis or possibly centrifugal forces, basically by Galilean invariant argument. And I have a gut feeling that those are not the important things. They certainly aren't the important things for spontaneous rotation, and I actually have a gut feeling that they're not the most important things in this term. But that's
I think that's a dangerous assumption, because if it does all arise because V is some nonlinear function of velocity, it might be that pinch term affects the kind of solutions that you can get out of there.
At any rate, my challenge is, for those folks who like these types of ones, my challenge is to think outside the box, because those types of things cannot explain spontaneous rotation.
No,
On their own, they cannot explain it. They may be part of the picture, but they cannot alone explain it. Okay. Now, moving on and talking about variations, it turns out that if you heat the electrons in the center of the plasma, in this case, these are results from D3D, you can change the picture. In D3D, in their ohmic H modes, which they rarely run, but they did specially for this experiment, they again find a positive, that's co-velocity, that is, in this case, relatively flat in the center of the plasma. However, if they heat these using ECRH, that's electron cyclotron resonant heating, they can produce velocity profiles which dip down, actually negative, in the center of the plasma. So if you heat the electrons, in this case by ECRH, in the center of the plasma, it can force the toroidal velocity more negative in the center. On CMOD, we also have lower hybrid current drive. Lower hybrid current drive is capable of changing the current profile. When supplied in the center, what it does is to lower the internal inductance, which means that the current profile is changing from peaked to more flat. And when that happens, we find that the central toroidal velocity is forced more negative. And in fact, you can produce velocity profiles which, before you turn on the lower hybrid current drive, are near zero, maybe slightly negative in the center. These are L mode, these are not H mode plasmas. But when you turn on and look when the lower hybrid's been going for a while, you've got a velocity profile which is quite seriously negative in the center of the plasma and hasn't changed terribly much at the edge.
You just hinted at something. Could you make it explicit? In L mode, you don't see any strange rotation effect?
No, this is an L mode case. Okay.
On what you were saying, that it's flat in L mode.
I'll show you an example of an L mode in a minute, which has some strange rotation. But the answer is there is rotation in L mode. It does vary with parameters, but it's, generally speaking, certainly not as positive as we see in most H mode cases. You can deliberately set out to change this rotation by doing what we call mode conversion flow drive. And this, I won't go into the details of how this is ion cyclotron heating in a regime where mode conversion is mostly taking place. In contrast with the usual case where we have minority heating, MH, where we have the toroidal velocity about maybe 40 kilometers per second. In these cases with mode conversion flow drive, one can approximately double the central rotation and force it more positive. The density in these two cases is essentially the same. There are some differences in ion and electron temperatures, but this effect, which has been discovered fairly recently, is something people have been looking for a long time. We don't know whether this is a direct momentum drive or not. There is approximately enough momentum in the waves themselves so that if this were truly directed and were deposited in the center of the plasma, it might be capable of explaining this difference. So it's not completely clear that this is spontaneous in the sense that I've been meaning here. But we also don't know whether this effect really is a change in the spontaneous rotation, or whether it's a direct momentum deposition. Now, here are again L mode. This is the answer to the question about L mode. These are, we also know that there is a density dependence. And there's actually a transition that occurs all within L mode. In fact, in some cases, in limited plasmas. This has been seen on very clearly on TCV, is the reference. But like TCV, we observe a transition from negative to positive rotation in limited L modes, governed in part by density and in part by safety factors. So here are 4 different plasmas where the Q profile is evolving as a function of time, and those 4 plasmas have different densities. Okay? And what you see is that for the lowest density plasmas, the rotation is pretty much always positive. For the highest density plasma, the rotation is pretty much always negative. But for the intermediate cases, systematically, there is a transition which occurs at some Q value between negative and positive rotation. These are all L mode, there's no H mode transition here. Okay? And so what this shows, and by the way, the changes, I haven't brought a profile, but the changes to the rotation occur only inside the surface corresponding to Q is about 1.5. Yeah, don't worry about it too much. That's simply the experimental fact, okay? So, but the main point is it's not changing at the edge. It's only changing in the core, in the central region of the plasma.
Were these sawtooth things?
Yes, they were. Okay, my time's just about gone. So let me finish with a couple of remarks, and I shan't trespass on the theorist's territory too much. But here's a way of trying to think about what the mechanisms are for toroidal momentum transport. What I've been showing you is basically momentum can be transported radially by particles or fields. What I've tried to argue is that the fields are, if they're perfectly axisymmetric, can't do this transportation, and that the degree of non-axisymmetry in CMOD experiments is small enough so that we can basically rotate, as far as we can tell, rule out these kinds of mechanisms for momentum transport. In which case you're left with particles. There can, of course, be neutral atoms, energetic ions, thermal ions, and so forth. There are various types of arguments. But I believe we are really down to the point where we're focusing on the rotation, spontaneous rotation arising from electrostatic turbulence. I don't mean that it is ITG, it could be lots of other things. That's just an example of a type of a phenomenon which might give rise to turbulent energy transport. There are some theories. Here's a list of a few of the key theories that have been put forward to try to explain spontaneous rotation. I'm not going to say much about them, except that as far as I can tell, there isn't really a focused confrontation between theory and experiment in this area, and I'm hoping perhaps this workshop will help to stimulate some. So let me finish with a summary, and then if there are any more questions, we'll take them. H-mode tokamak plasmas spontaneously rotate in the co-current direction in a scaling way that is consistent across different machines, although not exactly so. And as far as we can tell, this is truly spontaneous. It's not driven by auxiliary heating or anything like this. Also, of course, in the edge temperature barrier region, there are many mechanisms at work, and really we lack a proper understanding of that region too. This could be explained by many things, but the strong velocity gradients that occur in the core, even without direct momentum input, really show that there must be non-diffusive momentum transport. It's not just an edge barrier effect. The transients confirm the fact that there are diffusive effects with diffusivities that are roughly the same rate as heat. But altogether, these facts show that there is a mechanism which transports momentum up the velocity gradient to counteract diffusion in that simplified sense, heuristic sense. And I've argued that there's no reason to suppose that should be proportional to the toroidal velocity. I've shown you that electron heating can change things. It can make the center more negative in rotation. Density also is important. Energetic ion RF mechanisms might sometimes be significant, but they don't explain the ohmic results. we've seen unequivocal flow drive by mode conversion, but it's not proven whether that mechanism is really direct drive or whether it's modification of the turbulent transport mechanism. My own view is that the most plausible mechanism for explaining spontaneous rotation seems to be turbulent transport giving rise to Reynolds stress, but a quantitative prediction really is still lacking, in my opinion. Thank you very much.
Questions?
Yeah.
In fluid turbulence, there are examples of cases where small-scale turbulence, if it's non-parity invariant, can give rise not only to a turbulent diffusion, but to a first-order term, which is like called the kinetic alpha effect, analogous to in a duped dynamo problem to the growth of magnetic field. So in this case, you can drive large-scale flows under the assumption that the small-scale turbulence is non-parity invariant, which might be the case here. So
well, I think this would be, in a certain sense, the inverse of an alpha or beta dynamo, in the sense that an alpha or beta dynamo drives current. Here we have the opposite. Velocity and convection drives current. Here we have the opposite. We have sort of current and other gradients, and they're driving the flow. So I think, but I think that there may well be strong relationships between those types of mechanisms. Yeah.
When you showed the engineering scaling, as you call them, you told also that you were going to give a hint to the theoretical community to have a hint on the physics and to put the scaling on a more physical ground. But
well, that was really just
that?
To show it in terms of non-dimensional.
So is
parameters.
omega precession is what? What are you implying?
I'm simply saying that we can put it in non-dimensional quantities.
Oh,
here.
okay. So
That's
I thought you
That's
were.
all I meant. I didn't mean anything.
You were
subtle,
saying
no.
that
I'm not that
energy
clever.
over
Sorry, I'm not that
ID
clever.
is omega precession, or there is something
No,
magic behind that.
No,
Yeah.
there's no magic.
Fine.
You also had the plot where it was, I'm sorry, I'm going to get this wrong, megaamps per megajoule, no, megajoule per megaamp seemed to order.
Yeah, that's basically this
That's
right-hand
basically
plot.
this, okay.
That's basically this right-hand plot. It's slightly different, but basically that's it. I mean, it's not written like this, but if you do some arithmetic on this, you wouldn't be able to. But a lot of those guys out there can do the arithmetic on this and realize that it's essentially the same scale. Yeah.
Of course, you assume that all the spontaneous rotation from all these different devices is like driven by the same physics.
Well, I might have appeared to assume that, but I think your point is a very good one, that there could well be multiple mechanisms, and I rather suspect there are, okay? And so you're coming back to this argument about the so-called momentum pinch. There may well be terms that, that are proportional to V phi. My argument is they're irrelevant as far as spontaneous rotation is concerned, or at least they can't explain on their own, by any means, the spontaneous rotation that we observe.
But you have to be very careful if you start to compare one measurement at one device with another measurement.
I will try to be careful.
I think that there's a similar physics involved.
Well, of course, comparing different devices is a very important thing for us to get done, and so I'm here with sort of a message to theorists, which is, hey, take more notice of this. This spontaneous rotation is really interesting, and if someone could actually explain it and come up with the mechanism that is really it, it'd be really interesting. But I also would love to appeal to experimentalists by saying, we've spent a lot of time on CMOD, and I've mostly shown CMOD data. It's not that people are ignoring it on other machines, but I'd like to recruit more people to be interested in this. It's harder to study it on machines that are dominantly neutral beam driven, because as soon as you put neutral beams in, even if you balance them, you don't really know what the profiles of the momentum are, and so they aren't necessarily completely balanced. So it's less easy to do it.
I just wanted to comment on your last point about the most plausible or a plausible mechanism being this turbulent mechanism. There were some very nice measurements done on the linear device, controlled shear correlation experiment, UCSD, where they demonstrated experimentally with probe measurements in the edge that you did get a residual stress that explained an azimuthal rotation that was observed in the core. So it was kind of a self-consistent picture of an edge turbulent mechanism driving the core rotation. And it's, I guess the onus would be on the tokamak people to try to reproduce those types of measurements. There have been some efforts, but like you say, it's tricky because they have full electrostatic and density probe measurements in the end region.
I mean, obviously, one would love to go inside the plasma and have independent measurements of V tilde and phi tilde and so on and so forth, and you know how hard it is.
I want to add to some remarks that Ian made. It seems really, really important to me to understand the CMOD results for ITER. There's some focus in the theory community in understanding plasmas in which there are very strong rotation driven by neutral beams. But in CMOD, everything is driven by the gradients. The turbulence is driven by the gradients. Neoclassical, if it's there in any way, is driven by the gradients. It's all because there are gradients there. And that's what the spontaneous rotation is. It's really a naturally occurring rotation.
One last question.
The figure on the right, if you were to decompose the red and the green points into principal components, and then ask which of the principal components leads into the sort of outlandish predictions for ITER, have you done that exercise?
No.
What are we actually extrapolating here?
No, we haven't done that exercise, and I think we've already had some fairly cogent criticisms of this scaling. I mean, in my view, the scaling is not ready for extrapolation, and I don't believe those ITER points, at all. But they're just saying that's what you would get if you believe the scaling. Okay. I mean, I think we're doing the best we can, and we've got a long way to go. We need some fundamental understanding of what the mechanisms are.
But it was useful back when we were doing 0D predictions, energy confinement, to find what principal component was that was giving that large thing, and it turned out to be the most undetermined one, and it turned out to be rho star.
Well,
you can learn from the data by asking the question, what is important for that extrapolation?
Well, I mean, the studies indicate that if you want to boil it down to a parameter, it's beta. Okay, that as far as we know, it isn't rho star. Okay, I mean that's sort of the answer. But if you want to press me on these kinds of studies, I'm not going to try to defend that. Okay. That's what we think. I mean, this is work done by John Rice. This is basically where he's ended up. I think that there could be some more systematic studies done on this, but as I've said, my own view of this database is that it's skimpy enough and it's uncertain enough, and these effects, as I've shown you, are subject to lots of other perturbing influences that I'm not sure the extent to which I would believe it.
How essential is it for the ITER design that we have now that this will be true?
It's not essential, but it answers certain very important questions that people worry about, such as the stabilization of MHD modes. And if ITER is going to take advantage of, let's say, internal transport barriers, we not only need to know what its velocity is going to be, we need to know what the shear of the velocity is going to be, as Peter has been pointing out. So it could have very important consequences. I mean, in the end, we know that the velocity and its shear affects the transport very strongly in tokamaks. And yet, we're really only at the beginning of understanding what controls the rotation of tokamaks. So there is a sense in which this is really at the forefront of understanding tokamak transport and really part of the heart of that.
So the Mach number, like Peter says, in ITER it can be low, right? Not high enough for Keys transport barriers to be reproduced. Well, this scaling is not ready for extrapolation, and is this all a cause for worry? Well,
Well, ITER
the line on this?
ITER does not take credit for internal transport barriers in its base scenario. It takes credit for H mode, which we have a high degree of confidence we can produce in H mode, in ITER. So the quick answer is that, as far as we know, ITER doesn't depend on those types of effects. But to get a fundamental understanding of the transport, I think you have to know what drives and controls the rotation.
Well, with that, why don't we take a coffee break and reconvene at 11:30? Thanks again to both of you.